Today, software engineering models are rapidly evolving into autonomous, repository-wide agents capable of complex multi-step problem-solving. This evolution exposes a specific architectural tension. Developers require low latency speed for interactive line-by-line coding, while the model simultaneously needs deep reasoning to execute long-term planning. Composer 2, developed by Cursor Research, is designed specifically to resolve this bottleneck. The system aims to execute complex engineering tasks across massive, multi-file codebases without degrading context or losing the thread of the original objective. Operationally, the model must solve immediate problems for interactive use while maintaining logical coherence over a long time horizon. Addressing this dual mandate required a shift toward a specialized two-phase training architecture. Simply scaling up a standard large language model does not inherently produce reliable multi-step execution. A model may understand syntax, but still fail to string together the sequence of actions needed to reach a final goal. The core thesis of Composer 2 is a structural separation, isolating knowledge acquisition from behavioral execution. This uses two sequential phases. Phase 1 focuses on pre-training for foundational knowledge, feeding into Phase 2, where reinforcement learning dictates behavior. This ensures the model retains syntax abilities while learning forward-looking planning, requiring a training environment that perfectly mirrors its final deployment interface. When an agent is trained in an environment that doesn't match its real-world deployment, it suffers from distribution shift. The logic it learned in the lab breaks down when it encounters the friction of a real codebase. Composer 2 achieves its capabilities by pairing this bifurcated training with an exact replication of the developer's workspace. Examining the architecture begins with the raw baseline capabilities required for Composer 2 to operate interactively. Before it receives a specific task, the model possesses a foundational understanding of syntax and language patterns. This is its latent coding ability. Phase 1 injects massive amounts of raw code data into the base network through continued pre-training, expanding the model's internal latent space. This step ensures the model retains the low latency, immediate problem-solving skills required for daily interactive coding. A deeply mapped latent space provides the necessary vocabulary and contextual awareness for the complex reasoning the system will demand later. While Phase 1 builds a reservoir of technical knowledge, the model at this stage lacks the directional logic required to execute an extensive engineering plan. To move from raw knowledge to directed action, the pipeline transitions to large-scale reinforcement learning. The first target of this reinforcement phase is forcing the model to develop stronger reasoning. It must move beyond predicting the statistically likely next token and begin evaluating the long-term impact of its choices. The second target is accurate multi-step execution, chaining commands and discarding failed paths. The third is long-horizon coherence, traversing dozens of steps without losing the objective. This feedback loop rewards only a functional, compiling state. Pruning incorrect paths forces forward planning and self-correction. This process introduces a risk called reward hacking. If the training parameters are too simple, the model will find mathematical shortcuts to achieve the reward without solving the actual engineering problem. Using the friction of realistic coding problems prevents this. The complexity of a real software environment ensures there are no easy shortcuts to exploit. Reinforcement learning is the engine that converts a static repository of code knowledge into a dynamic engineering agent. Grounding this reinforcement phase in reality required a specific structural solution. Cursor developed the harness, a training infrastructure built to perfectly mirror the actual IDE the end user operates. Providing equivalent tools and structures during training minimizes distribution shift, allowing multi-step plans to translate reliably to the final product. The team sourced training environments designed to match real software engineering problems, rather than using synthetic tests. To ensure sufficient complexity, Cursor utilized their own codebase as part of this realistic training environment. This environmental symmetry reduces the errors that often occur when a model leaves a lab setting and encounters an unstructured file system. An agent can only master a complex toolset if its reasoning is forged inside an exact replica of that toolset. The results of this bifurcated training and harness alignment are verified through empirical testing. Internal evaluations show a major performance jump. Composer 2 achieves a score of 61.3 on CursorBench accuracy, derived from real software engineering problems to test actual deployment viability. On public benchmarks, it scores 61.7 on Terminal Bench and achieves 73.7 on SWE-bench Multilingual, alongside state-of-the-art frontier systems. These metrics demonstrate that the two-phase training architecture successfully bridges the gap between interactive speed and long-term autonomy. The development of Composer 2 provides a specific architectural takeaway for specialized AI. To achieve true agentic behavior, knowledge acquisition must be structurally isolated from behavioral reinforcement. Improving specialized AI will increasingly require domain-specific training infrastructures rather than simply larger datasets. The next phase of software engineering relies on the tight integration between the model and the interface it operates within. Composer 2 demonstrates a process for developing specialized agents that bridge the gap between static knowledge and reliable engineering execution.